Okay, this is Weka Week 4, answers to the homework questions. So, talks about setting a random seed, affects which random sample from the data set will be chosen for training. So how do we change the seed? So we go to here and here. You can change the seed here. Number 2, at minute 4:17, we see that he got 10 different results for the accuracy of J48. Why are there different results? So you can see there are 10 different results here. And what he did is he just changed the seed, and then repeated the training. So each time he's going to get a different accuracy. The idea is that if we randomly select a sample and do training and testing, we'll get an accuracy, but if we used a different sample, we may get another accuracy, and so maybe the best idea is just to repeat it several different times and then take the average of all those accuracies and report that as the best estimate of the accuracy of the model. Okay, this is about the baseline accuracy, concept of baseline accuracy, which is what the 0R Weka classifier does. So in the weather, for example, in the weather nominal data set, the class is whether they play golf or not. And if you look at the data set, there are 14 elements, and 5 of those elements they do play golf, and 9 they don't. So if that's all you knew, then if somebody new comes along and you want to predict whether they're going to play golf or not, you would just say, well, since in the past they played 9 versus they didn't play 5, or sorry, the other way around. They didn't play 9 versus they did play 5, you would then predict that this new person wouldn't play because that's called the majority class of the golf data set. And regarding question number 3, which classifier behaves like the guessing we made here? We just said that's the 0R classifier. Okay, if you look around minute 6, you find the answer to this question. He shows that with a certain data set, many of the algorithms do worse than the base learner, do worse than the baseline, do worse than 0R, and he just showed a bunch of them. So for example, this one, the lazy IBK, only gets 38%, but I think the baseline was something like 63%. So it does worse than the baseline, or worse than 0R. So that is the answer for number 5. Okay, the next question actually was a mistake, should go in this video. And it says he repeated the experiment 10 times, and standard deviation. So we just said earlier that if you look here, he repeated it 10 times, and we can calculate the mean of this, and that's a good way to estimate the accuracy of the algorithm. But the other thing you can do is you can say, well, how much variation is there in these numbers? Let's suppose if I look at these numbers, the mean is about 94. So suppose the mean was about 94. Let me check that. The mean doesn't tell me. Here, the mean is 94.9, so almost 95. Okay, so let's say the mean was 95. Now we can see that there, sometimes it's obviously above 95, sometimes it's below 95. Here it's a little above 95, here it's more above. So there's some variation in the data around 95. But there, maybe 1 or 2 percentage points above, not even that, and 1 or 2 percentage points below, not even that. But you could also have a case where instead of these numbers, maybe you got numbers like 85, let's say 90, sometimes you got 90s in here, and sometimes you got 100, and sometimes you got 91, and other times you got 99. So the mean might still work out to about 95, but the variation is much greater. So that kind of points to kind of a less accuracy or less confidence in our predictions than in this case where it's very close to 95. Maybe you don't necessarily agree with that statement, but anyway, there could be more variation around 95. And that's what this measures. The sigma is the variation around 95. So we're also interested in the variation around 95. So again, this question 6 actually it refers to this video here. And what was the value of the variance of the estimate? So that was this number, whatever it was here, 0.018. Okay, let's talk about cross-validation next. You can see 2 pi's. What are they? Let's see that. So here we see 2 pi's, and this is explaining the idea of cross-validation. So you take the whole circle represents the entire data set, and you split it up into usually 10. We call them folds, 10 folds. And then you take one of them out, and you do the training on the rest of them, and test on the blue one. And then you get an estimate of the accuracy, and then you repeat it again, but this time you take a different slice out for testing, train on the other ones, and you do that for all 10 slices. You hold out that one of them for testing, and then you can average all of the estimates of the accuracy to get the sort of most realistic estimate of the accuracy. Okay, let's see. Okay, so there's 2 concepts here. One is to measure the accuracy, and the other is to have an algorithm, or a model to use in the future. So if we want to make our model, we may as well use all of the data to make our model. We're going to use it for future data that we don't have right now. So we may as well make our model with all of the data, but we saw that we don't, that's not exactly how we measure the accuracy of our algorithm. So we just said how we measure the accuracy is, for example, tenfold cross-validation. So that we just explained that. But to build the algorithm for future use, as I said, we may as well use the entire data set, and that's what he means by for deploying the model, for using it in the future. We use the whole data set. So that's what he means here. Okay, in this video, this is the next video, here we have the holdout method, and he's holding out 10%, and then as we said, we could just set a different seed, and we'll get different results. So he gets 10 different results here, and he can average them, and the average turns out to 74.8, and the standard deviation turns out to 4.6. Okay, so what is meant by a fold? We just saw that the folds are those pie slices. And then one more thing here we should mention, a little bit surprising. So here's what we did. Here's what we got when we did that holdout. So we got the average was for this particular data and this particular model is 74.8, and the standard deviation was 4.6. So again, what the standard deviation means is that Sometimes we might get something like 74 right in the middle, but we could get like 74 plus 4.6, which would be like 78 or 79. We might get something like much smaller, smaller than 74, like 74 minus 4, which would be around 70. So we're saying we could get things like 70 and 79. So there's quite a bit of variation there. On the other hand, when we do the cross-fold validation, if we could actually look at it, I don't think we can see what the results are like this, but if we do it, here we'll get maybe basically the same as we got here, but the standard deviation is much smaller, and that's a good thing. We want the standard deviation to be small, and it seems to be a lot smaller. And so what's the possible reason for that? Well, remember, in cross-validation, we are testing on every single instance, because first we take out one slice, then we take out another slice, then we take out another slice, and we're going to get through all of the slices, so we're going to get through the entire pie. But here, it's not quite guaranteed that we're going to do that, because we're just randomly selecting 10% for testing, then randomly selecting another 10% for testing. It's not clear that we're going to get, for example, we're never going to repeat like what happened in this test. There might be some of the data points might appear in here, and some of those might appear in here, and so on. Whereas that will never happen here, because we're literally splitting the data set into 10 different ones and only choosing a slice for testing only once. So that, I guess, is the reason why this turns out to have a higher variance or standard deviation than this. So cross-validation, although it seems like it's the same thing as holdout, when you hold out 10%, but it's really not, because here we're guaranteed to be testing on every single value in the data set, whereas here we're not really guaranteed of that. And somehow, I'm not quite sure how, that leads to a smaller variation here, smaller standard deviation.